Okay, so let's continue. And now we want to come back to causal fermion systems. And first of all, I want to explain that we can use the same method which we used in Minkowski space to construct a causal fermion system. We can also use this on a Lorentzian manifold. So let just Mg be a Lorentzian manifold. And I need to assume that it is spin, of course, but also that it's globally hyperbolic. And I don't want to hyperbolic. So I don't want to say what this means technically. I don't want to give you a definition, but just what it means in our context. So this means that if this is our space-time, that there is a Cauchy surface n, and Cauchy surface means that if we take any initial data on n, that then there is a unique solution of the Dirac equation to the future and to the past. So in the Dirac equation, I just write it as just explained. So we assume that there is a unique solution. And in fact, like if the spacetime is not globally hyperbolic, then the construction does not work, or at least not in a straightforward way. And this makes the situation more difficult, and in fact, most questions are open. Okay, so let's assume this, and then we can introduce the Hilbert space of solutions. Namely, we can identify the solutions with the initial values on n. So we just take psi restricted to n, and we take the scalar product psi phi as similar as what I just introduced, and we just integrate over n. So just psi mu j gamma j phi d mu n, and this makes the solution space to a Hilbert space. And now we again choose H as a closed subspace of this Hilbert space. Then we again need to introduce some regularization operators. Let's call them R epsilon. These are mappings now from H to the continuous sections of the spinor bundle, to the continuous wave functions, with some additional properties similar to the way we did it on Tuesday. And then we can introduce the local correlation operator just as before. So we just say f epsilon of x psi phi. Here we take like the Hilbert space scalar product is defined via the relation that this should be the same as R epsilon psi of x R epsilon phi of x, and here we take like this spin scalar product at the point x, and I think there was a minus sign. Okay, so this defines the local correlation operators, and this is in fact like an element of curly f. So therefore, the f epsilon is a mapping from the Lorentzian manifold to curly f, and now we can take the push forward measure of mu, where mu is just the volume measure on the Lorentzian manifold, the square root of minus determinant of g times d for x. And this gives us a causal fermion system. So this works just as before. And the whole construction is generally covariant. It does not depend on the choice of the Cauchy surface and so on. Well, and now there are two questions which we are interested in. The first one is like, what about the causal action principle in curved space-time? And the second question, which is of course kind of a little bit related, how do the geometric structures of a Lorentzian manifold show up in the causal fermion system? So what is there like an intrinsic definition of connection and curvature in the causal fermion, on a causal fermion system? And what is the connection to the geometric structures on the Lorentzian manifold? Okay, these two questions is what I will address both of these questions after each other. So let's start with the causal action principle. And there's a limitation at the moment, so that the formalism of the continuum limit has been worked out only in Minkowski space. So therefore, I can't show you anything on the Lorentzian manifold, but this is not for principal reasons, it's just because it's not yet worked out. So the main additional difficulty is that, I mean, in the continuum limit analysis, it was we analyzed the singularities on the light cone, and this was just a light cone in Minkowski space, and therefore we could also use Fourier methods and so on to analyze the behavior in detail. On the Lorentzian manifold, the light cone structure is kind of more complicated because it is spanned by the light cone is generated by all null geodesics going through a spacetime point P. And I mean, the light cone expansion has the light cone expansion generalizes to the Hadamard expansion here on the Lorentzian manifold. However, how to regularize this Hadamard expansion in general is not so clear, and how to form composite expression, and how to evaluate weakly, and how to analyze the asymptotics as epsilon goes to 0, all this has not been worked out. And therefore, the only thing we can do at the moment is stick to Minkowski space and consider linearized gravity. A linearized gravity means that our Dirac operator has the form of a linearized gravity in general means, so we take for the Lorentzian metric, we write it as a Minkowski metric plus a deviation and hjk, and this is treated just linearly. So we only take linear deviations from the Minkowski metric. And then if you compute the corresponding Dirac matrices and so on, what you find is that the Dirac operator can be written as follows. First of all, I mean, there's like a Minkowski Dirac operator, and then plus a perturbation. Again, write B, but now the B is a differential operator itself. It's something like I over 2 hjk gamma j d over dxk plus lower order terms. And also, I mean, the way the Dirac operator looks like depends on which gauge you have chosen and so on. But that's not so important. I mean, the only thing I want to point out is the differential operator of first order. And then the question is like, what does it mean small? I mean, can it really be treated as linear in a linearized sense? And this is a little bit tricky because if you consider first, if you have a differential operator as a perturbation, this basically means that the singularity structure will change. And this is also kind of obvious if you think of, I mean, gravity is diffeomorphism invariant, and then what happens here to first order is that the light cone is deformed slightly because the causal structure is modified. And therefore, if you have something singular and you kind of move this a little bit, this is described linearly by taking derivatives. So if you kind of differentiate the singularity, then you get something which is even more singular. Yeah, Simone?
So are we requiring that H satisfy the linearized Einstein equation?
No, not yet. Yeah, good point. So I mean, right at the moment, so no. So we do not impose the Einstein equations. This is similar to our procedure before when we considered an external potential. Also, the potential was arbitrary, and only at the end we got conditions for the potential. Okay, so therefore, I mean, what I'm just what I want to say is that this is not a convincing procedure, because since the singularity structure changes, one should treat this non-perturbatively. But what one can nevertheless do is you just take the corresponding formulas and then you compute the corresponding closed chain. You just compute AXY, and then you get also singularities here. And the good news is that all these contributions which come from this infinitesimal diffeomorphism, like this change of the causal structure, they drop out. Well, and the reason is because this whole setup is generally covariant. So this means in this AXY, the leading singularities drop out, and then what remains, or in particular if you say, well, in fact, the AXY really depends on the choice of gauge and so on. Suppose we consider now the eigenvalues, like lambda, the eigenvalues of the closed chain, where C is again L and R, and S is equal plus or minus. Then these eigenvalues do not depend on any gauges, and here the leading singularities drop out, and what you get is terms which involve curvature quantities. And as I said, the fact that it's all, since the whole framework is generally covariant, it is clear that what you get must be expressible in terms of curvature in the end. So if you get something which is not covariant, there's just something wrong. Then we made a mistake. Okay, but of course, since we only consider linearized gravity, we only get terms which are linear in the curvature tensor. Quadratic terms in curvature would, of course, go beyond the linear approximation. So therefore, all I'm saying now is modulo higher orders in the curvature tensor. Okay, so therefore, and yes?
So maybe, like if I get the linearized version of the curvature tensor,
Yes.
there's only one way to build the nonlinear version, right, up to R squared.
Yeah, exactly. They're basically like the curvature tensor consists of these derivatives of basically when you can say the Riemann tensor, say symbolically something like the derivative of Christoffel symbols plus Christoffel symbols squared. And once you know, and then you can expand this in powers of the metric or of this H. Once you know, the first order terms, which is basically like, then you know these guys, and then the others are determined. So therefore, it's determined up to really higher order, like higher powers in the curvature.
So I'm asking this because maybe right now the impression is that you really only, like you get out only linearized Einstein equation.
Yes.
But if I'm not mistaken, then you know, like you have to, since everything is covariant, you explained that to me. So
Yes. So exactly. This is you're right. It's a bit more than maybe what one would call linearized Einstein equations. One gets really Einstein equations up to corrections of higher order in the curvature tensor. And then one can also think of how do these correction terms, I wanted to say this later, but since we are just talking about this, suppose we have something like the Einstein equations, so like Rij minus 1/2 R Gij is equal to kappa times Tij, and then there are plus higher orders in the Riemann tensor, something like this, Riemann squared. Then the question is, how could these correction terms look like? And in particular, what is the scaling which comes up? The Riemann tensor has the length dimension 1 over length square, simply because second derivatives come up. So therefore, this has dimension 1 over length squared. The kappa has dimension 1 over length squared. And now, in other words, if it's a higher order term in the Riemann tensor comes up, it must of course be dimension. So we have to put in something like, this must always come with a factor of dimension squared. So therefore, for example, the question then is, what could have the dimension of 1 over length squared? This would then be, for example, m squared. And m is like the masses which come up. So this is like a kind of dimensionless quantity. No, sorry, I made it wrong. It must be 1 over m squared. M has dimension 1 over length and the Riemann has 1 over length squared. So I mean, this would be like a reasonable correction term. Like, I mean, for example, one could have a correction term which would be something like the scalar curvature over M squared times the Ricci tensor, something like this. I mean, this would be quadratic in curvature and would have the same scaling behavior. So the kappa would again be scaling dimension 1 over length squared. This is a dimensionless quantity and so on. So such corrections could appear in principle, but if you look how small they are absolutely tiny because basically because the curvature is so small. So I mean, if it would have to come up with like a big prefactor in order to have a noticeable effect. So this means like with such consideration, one can convince oneself that if they are correction, they are much smaller than what you could observe. Okay, and with this, I mean, with this in mind, let's just, as I said, we must do it anyway, so we just restrict attention to linearized gravity, and let's just see what one gets if one goes through the detailed computations. This is kind of the end result of these computations. Namely, I see. So I mean, maybe first of all, let's write down again what the Einstein equations, what the Euler-Lagrange equations look like. And this is now in this setting where we have neutrinos. This is where this is worked out in the book. But in fact, it works the same way for the model which involves which we had for this as a standard model last time. So this kind of physically realistic model. So then this delta Q has this form. And these matrices K, which come up here, they are similar to this K which we had in the simplest model where I had kind of written this down in detail. So this is where kind of the differences of the absolute values of the eigenvalues come up in their first order perturbation.
That's not R.
Was it R?
It was R.
Okay, you're right. I mean, you're right. So we had like this kind of R for the model which only involved the charged leptons, so this one sector model. And here this plays a similar role, and since we have like two sectors, we have like also this sum over n here. N is 1 or 2. Okay, but this is not so important. I mean, what the important thing is how do these k's look like. So roughly speaking, in order to satisfy the Euler-Lagrange equations, so this k should be a multiple of the identity matrix. I mean, if all these k and c's are the same, then obviously you get 0 here, and then and only then are the equations satisfied. Okay, now how does this k look like? So this looks as follows. Okay, let's just go through the different terms. I mean, first, this is like the contribution involving the energy momentum tensor, and R and L, this corresponds then to the right and left-handed component. Energy momentum tensor of the Dirac field. Yes?
So did you already replace the linearized version of the Einstein of the Riemann tensor?
Well, I mean, I just rewrote the linear contributions in a covariant form, and this is like what gives these curvature tensors. Okay, and then one has here terms which involve the Ricci tensor. Okay, and there is one term here, which is kind of the leading term, because we have here P0, like this is the most singular term. I mean, you should say maybe this K16 and I see also, okay, so this K16 like this and K8. So these are again these simple fractions which have a rather complicated form, but it's, well, not so important how they precisely look like. In any case, so these are some simple fractions. Okay, and then so this is kind of the leading contribution. And this is a contribution which we can neglect. This is why I wrote here degree equal to 4. So this is of lower degree and can be neglected. And then there's here a contribution. This is where this delta comes into play. And delta was the energy scale of these non-trivial regularization effects. I mean, if you recall yesterday, so when I talked about the regularization of the neutrino sector, I said, okay, we have like here our Dirac-Cs, like this is the scale 1 over epsilon, and then there could be here like this general surface states, and there could be like this shear state, and this was on a scale 1 over delta. And so delta is a length scale which is much larger than the Planck, than epsilon, but which should still be much smaller than the macroscopic length scale. So this is what the delta is. And the delta is precisely what comes up here. Okay. And good. Now, this K here should be a multiple of the identity matrix, roughly speaking. Well, and what about this term? I mean, first of all, I mean, one might ask, why do we need to introduce one gravitational field? I mean, we could also say in the first sector we introduce a gravitational field, and in the second we don't, or in the second we change a different one. And in this case, the action gets very large, so this is forbidden. And the reason is that when the gravitational field kind of deforms the light cone a little bit, and if in one sector the light cone is deformed different from the other sector, then the eigenvalues will no longer coincide. So they will be completely different because they have singularities at different space-time points. And then if you think of the form of the Lagrange, and we had this lambda I minus lambda j absolute value, I mean, this is also what comes up in the Q. Say Q is equal to this times some additional terms. This here will get extremely large, and there's no way this is going to be a minimizer. So this tells us that really the gravitational field must be the same in each sector, but then this contribution here is proportional to the identity matrix, because, well, it doesn't depend on the sector index anymore, and therefore this contribution drops out, which is kind of good news. So kind of, namely, okay, so this is gone, and then we are just left over with this contribution here, the one which involves 1 over delta and the energy momentum tensor. And those two can in fact compensate each other. The good thing is that this K16 here, this has the same degree on the light cone as the K8. So therefore, when we evaluate weakly away from the origin, they just give the same scaling behavior in epsilon, and therefore we can let epsilon go to 0, and they just give some real coefficients here. Okay. And therefore, what you get in the end, I think that's the end of the transparencies, but I can still leave it there in case you want to have a look, is just something similar to the Einstein equations, but not quite. Let me just write this down. Maybe I'll go to this side of the blackboard. But one should keep in mind that here both tensor indices are contracted to psi, and psi is a vector on the light cone. This means what one gets is, if we set these terms equal, so we just get Tij is equal to one over delta squared times Rij, but only if we multiply the whole thing with psi-ij. Let's write it like this, plus, and then we have like here one constant, here we have another constant. They come from these regularization constants, times psi I, psi j, should be 0 for all psi with the property that psi squared is equal to 0. Because we evaluate on the light cone, and therefore this is a null vector. Okay, then one is tempted to say, well, if this is true for all vectors, then the tensor should better be the same, but this is not quite true, because here we can add something, any constant, say C3 times the metric, without changing anything, because the metric contracted, if you contract the metric with psi I, psi j, we just get 0. But in fact, apart from this freedom, the tensor here has to vanish. So what we get then in the end is like, well, in fact, in particular, we can replace this Rij by the Einstein tensor. Because we can, of course, also just replace this by -1/2 scalar curvature times the metric, because the metric part drops out anyway. So then we get like, so what we get is like the Einstein tensor, so Rij -1/2 Rgij is equal to kappa times Tij plus, and then we have like here cosmological constant times Gij, and a priori this is like a constant which depends on x. And kappa is, well, you can just compute this, so this is in any case, this is like delta square times these different constants. What was it, delta square times C1 over C2 or something. So this is just like a regularization parameter. This is just a constant which is dimensionless, and you see that the dimension comes in terms of this length scale delta. So therefore, if you say this is of the order 1, then this here should be of the order of the Planck length. So therefore, delta is what should be identified with the Planck length. And epsilon was even smaller. Remember this. So this means like we could say like epsilon could be the Planck length, but it could be on the Planck scale, but it could also be much smaller than the Planck scale. And delta is what determines the gravitational constant. Yes? If you let delta go to 0, exactly. So therefore, one procedure to make this kind of clean here is to say I keep delta fixed and I let epsilon go to 0. Yes, so this is like the scale on which these non-trivial regularization effects come into play. Yes. Yes. Well, just simply because, well, I mean, now we have to go back to this physical picture which we had earlier. I mean, that epsilon should not be 0. Epsilon should just be a very small positive parameter which tells us about the regularization of our space-time. And the reason why we considered families of fermionic projectors, families of measures, and then took the limit epsilon to 0 is just a mathematical idealization which takes care of the, or which wants to make use of the fact that epsilon is much smaller than the typical length scales. Yeah, exactly. And here this is really important because if we take the limit epsilon and delta going to 0, then the coupling constant is out and we just have the vacuum Einstein equations. Okay, and as I said, I mean, this can even be done in a clean way mathematically by saying I fix delta and let epsilon go to 0. Well, to me, this is not quite what the physical picture is. In fact, my intuition is that these should come that delta and epsilon should be of the same order of magnitude, like as I showed it here on the picture. And if you do this, then epsilon, of course, is what determines the gravitational constant. Because why should there be two different scales? But of course, this is just, well, first of all, it's speculation because we don't know. And also, it's not important for what we do here. So from a mathematical point of view, it might be best to just fix delta, let epsilon go to 0, and then everything is well defined.
Can you remember
I see, good point. I mean, this is something, I mean, in fact, the way, why does the energy momentum tensor come up here and so on? I mean, the way it works is as follows. I mean, we have remember that the current, Jk, this is like psi and then gamma j psi. Okay, and this is something you can write if you think that if you think that's the fermionic projector. This is just the C contribution and then minus psi of x, psi of y. So we have like this bracket notation, if you wish. So therefore, this current can also be obtained by saying if you take the trace of gamma j times p of xy, p of x comma x, p of x comma x, this just gives me the current jj, well, and then plus these infinite counter terms of the c and so on. So this is just the Dirac current. Now comes the energy momentum tensor. So what the idea is now, I mean, what in fact in this qx comma y, the two arguments x and y are not the same. We only take them very close to each other. Yes? Yeah, sure. I mean, of course, in principle, we should put an epsilon everywhere. I mean, basically, like, of course, like a priori, if you do this, then these counter terms or whatever, this is like infinite contribution, which you need to subtract or something like this. I mean, I just want to focus on this contribution to the fermionic projector, which comes from the, say, particle state, like a particle wave function. It looks like this, and then if you take your trace, this gives you the Dirac current. But in the q of xy, in fact, we don't set x equal to y, but x and y are two distinct points. And therefore, what comes up here is in fact something like the trace of gamma j times p of xy. This is like what you need to consider. And if you again just consider the contribution by the Dirac current, maybe let's write it like this, you get some, or by the Dirac wave function, you get something like psi of x. In fact, this is, let's see now, psi of y, gamma j, psi of x. So this is what you need to consider. And now we expand this in a Taylor series around x. So this means we write this here as just psi of x, gamma j psi of x, which gives us the current, plus, and then just the psi k times dj psi of x, gamma j psi of x. And it turns out that this expression is in fact very close to the energy momentum tensor. Namely, let me just write down what the energy momentum tensor is. The energy momentum tensor of this Dirac field is just the real part of psi gamma j I dk psi, and then we have to symmetrize here. So this is how the energy momentum tensor looks like. And then, okay, here we have, it has the same structure. The only difference, it's not symmetrized, and also we don't have the real part. Let's see. I see. So this should be a k, right? Thanks. Okay, so but basically, this symmetrization comes into play once this index is also contracted with a psi. I mean, you see here everything is contracted with a psi anyway, so it gets symmetric automatically. Well, and the fact why the real part enters is because there's not only this guy coming up, but also it's adjoint, and then you have to look how they combine and so on. Okay, this is how it happens technically. So you see that basically like the fermionic projector contains not only the current but also the energy momentum tensor. A good point. I mean, in what I explained, yes. And then the question is, does the gauge field also give rise to an energy momentum tensor? And the answer is yes, and I computed this in the book. And this is, in fact, the computation is a bit difficult, well, because it's like quadratic in the gauge field. I mean, the energy momentum tensor of, say, the electromagnetic field. So this is like this. How is it again? Also F, J, A, F, A, F, F, I, A minus the trace, something like the trace-free part of this guy. So therefore, it's quadratic in the bosonic potential. So you have to do perturbation expansion, perturbation conjugations to second order, and then see what you get, and so on. Well, no, the C does not enter. So you would no. I mean, there's an additional contribution which has the correct structure, so it looks like the energy momentum tensor, and this comes with some new regularization parameter, different from all the ones we had before. And then you need to say, in order to get consistent equations, I mean, in particular the Einstein equations, well, I mean, in order to get to be able, at least in order to get mathematically consistent equations, so ones for which you can solve the Cauchy problem, then you need to choose the C such that it is compatible with the corresponding currents and so on, and this determines this additional regularization constant. So this is how it works. So therefore, yeah. But of course, it was important to verify this. And this is, in fact, the last thing I did in the book, because it was the most painful part of the book. Okay, so this is how you get the Einstein equations here. And, I mean, are there any more questions on that? So then I wanted to explain a little bit what are the geometric structures of a causal Fermion system. I see then we should also switch this off. What are the geometric structures of a causal Fermion system, and how are they related to the geometry of the Lorentzian manifold? And to this end, I mean, this is like a joint paper with Andreas Grotz, who worked this out in his PhD thesis a few years ago. And let me just outline how this goes. I mean, and again, I don't have time to enter the details, but I hope I can convey the general method and also show you some of the results. Okay, so this means we again return. So this is now the geometry, let's call it here the geometry of causal Fermion systems. Or in fact we call it a Lorentzian quantum geometry is what we call the paper. So as I told you, this is like together with Andreas Grotz. And the starting point is, again, as usual, so let H F rho be a causal Fermion system. And let's simplify the setting right from the beginning, because that's the only case which has been considered yet, namely, first of all, of spin dimension 2. In other words, we have like Dirac spinors in mind. And moreover, we assume that it's regular in the sense that the, assume in the sense that x of h has rank 4, so the maximal rank which is kind of allowed for all x in M, and M of course again is the support of rho. Okay, so this is like the starting point, And then at each space-time point we can have our spin space as usual. And then we have the kernel of the fermionic projector, which kind of relates different spin spaces. So this was pi xy, so mapping from restricted to sy, from sy to sx. So this is like our starting point. And then you could say, well, this structure looks a bit similar to has similarity to the spinor bundle which we had before, namely we have like a space-time. Well, it's more general here, just a topological space, but so what? I mean, this is similar to a manifold. And at each space-time point there is attached a vector space, so this is similar to a vector bundle. In fact, one could make this precise and say the structure so far is that of a topological vector bundle. And I mean, if you're, in case you're interested, I mean, this is written in this paper with Nikki Kamran, so where we work out all these more topological aspects. In any case, something important is missing here, namely Clifford multiplication. So what are Dirac matrices and what is Clifford multiplication and all of this? And this is something which is not there a priori, and then you can write down a definition. And then the question is, well, does this determine is this a reasonable definition? And also, of course, I mean, we do, in all the construction, we do not want to put in an additional input. I mean, we only want to work with structures which are inherent in the causal Fermion system in the sense that we only want to use information which is already encoded in the causal Fermion system. So we don't want to introduce some new structures ad hoc which carry geometric information or something like that. This would not make any sense. But still, I mean, the starting point, just to understand what one could do or what the idea is, is that of a Clifford subspace. How does this work? I mean, we have like this spin space, then we have the linear operators on the spin space, and we have the symmetric linear operators on the spin space. So this sim Sx, so these are the symmetric linear operators. On Sx, and this is then in fact a real vector space of dimension 16. So it's a 16-dimensional real vector space. Okay, now one can consider subspaces of this vector space, and let's call it K. So K sim of Sx. So let K be and let's just restrict attention like to physical dimension 4, although I could also do this in dimension 5, but I don't want to go into this here. So let's assume this is a 4-dimensional subspace with the property that kind of the anti-commutation relations hold. So namely that u comma v, the anti-commutator, is a constant times the identity. And a constant of the identity means that we can always write it as in the form u comma v times the identity. And, okay, this anti-commutator then also defines what this is. And this should be where this is like an inner product of signature, say 1, 3. Is an inner product okay. So this is just a definition. I should say now here you can play around with different dimensions, and you can ask the question, does this only work for 4 dimensions or are other dimensions possible? Also, is the signature here fixed, or could you take different signatures and so on? And we looked at this systematically, but maybe that's also not so much the point of interest. So let's just stick to the kind of basically like what we want to have. So we want to have a Lorentzian kind of Lorentz, you get the connection to a Lorentzian manifold, so this should correspond to the Lorentzian metric, so it should have signature 1, 3. Okay, I mean, this is like, the problem with this definition is that there are many such Clifford subspaces, which is of course also not so surprising, because we saw also before that there are many representations of the Dirac matrices and so on. So the problem is there are many choices of K, and of course then it's not clear which choice do we take. I mean, if we do make arbitrary choices, then we might run into problems later because the results might depend on how we choose these subspaces. And well, maybe I should have written this down, in fact, a little bit differently. So the definition is that this U comma V is a multiple of the identity matrix for all U and V in K. And then we can use this intercommutator to define this inner product. So this is like proportional to the identity on Sx for all U, V, and K. And then we just define U comma V as 1/2 the intercommutator of U comma V. Maybe that's better. And then this bilinear form, or this inner product, should be of signature 1, 3. Or this bilinear form should be non-degenerate and be of signature 1, 3. Okay, and the problem is like there are many choices of K, so what can we do here? And well, the strategy is, first of all, try to find a smaller class of such Clifford subspaces. So try to kind of fix the freedom partially. And then we still have classes of such Clifford subspaces, and then we have to work with equivalence classes. And in the construction later, always choose appropriate representatives and transform from one Clifford subspace to the other Clifford subspace and so on. And if you do this properly, everything works out in the end. But let's just explain this step by step. So the first step is consider specific Clifford subspaces, and the idea is the following. Namely, we have the operator X to our disposal. X has 2 positive and 2 negative eigenvalues, because it's all regular. Has 2 positive and 2 negative eigenvalues. And therefore, there is an operator, a unique operator, which we denote by Sx, which with the property that it has eigenvalues. So this has eigenvalues plus or minus 1. And the eigenspace corresponding to plus 1 is the same as the eigenspace corresponding to the positive eigenvalue here. And the eigenspace to minus 1 corresponds to is the same as the eigenspace of the negative. With eigenvalues plus minus 1, and let's just write it a bit simpler to save some time, and has the same eigenspaces, and then with the correct signs. So this means like plus 1 corresponds to the positive eigenvalue and minus 1 to the negative eigenvalue. Okay, this is then uniquely determined, and this is what we call the Euclidean sign operator. Generally speaking, what does it mean, sign operator? Well, sign operator means if we square this operator, is equal to the identity. So it just has eigenvalues plus minus 1. This is what we mean by sign operator. Yes?
The inner product departing the top, it should be non-degenerate.
Yes, this is what I mean by inner product. I mean, like, inner product, I mean like a bilinear form which is non-degenerate. I mean, okay, there might be different definitions, but that's what I'm using. Exactly, that's part of the definition. So the non-degeneracy is also not it must be part of the definition. Exactly. Okay. We'll see soon. In some sense, it's one representative of the tangent space. So, well, the good thing is, like, since this x square, this x Sx, the square is the identity, you can say, okay, this satisfies the intercommutation relations over here in the trivial setting. I mean, like, Sx intercommuting with Sx is the multiple of the identity. And therefore, it makes sense to extend Sx to a Clifford subspace. And this is what is called a Clifford extension. And so a Clifford extension is a Clifford subspace which contains Sx. And in fact, then one can show that there are such Clifford extensions, but unfortunately there are, again, many of them. But the nice thing is, at least, I mean, this non-uniqueness can now be described in the following way. I mean, like, if K and K tilde are Clifford extensions, then we can get one from the other, so then by a unitary transformation, namely just e to the I phi Sx. So we take kind of the corresponding unitary operator times K tilde e to the minus I phi Sx. In other words, there's the family of such Clifford extension is just described by an angle phi. And now we divide this angle out. So this is now the idea. I mean, so basically, like, then the Tx is like the set of Clifford extensions modulo the action of this group here, which is just like the U1, of course. I mean, this is like the U1 in a specific representation, and this is divided out, and this is what the Clifford extension is. Yeah, this is what the tangent space is. Well, and first of all, I mean, what's nice is the tangent space carries an inner product of signature 1, 3, so you can say this is Minkowski space locally. What is not so nice, it's like a whole equivalence class. And moreover, what's missing right now, there's no connection to geometric tangent vectors. I mean, usually tangent vectors are defined by, for example, equivalence classes of curves which have the same velocity vector at a given point. And then usually in this mapping which we had before, like for this Clifford multiplication, this was a mapping from the geometric tangent space to this sim Sx. Okay, and this is something we don't have here, because suppose we have like a curve with a velocity vector. How should we associate to this curve a specific linear operator acting on the spin space? So this is also something which is missing here at the moment. Okay, so this, excuse me? Yeah, exactly. In the end, yes. But right now, this is not so. This is something which is like, well, I mean, this is just, well, we are still at the beginning of the constructions. So, now let's suppose we want to now construct a parallel transport of spinors, say. So we want to have like, I mean, we want to have it of spinors and also of tangent vectors. So what is the goal? At least, I mean, that's our next goal is the following. Now we choose like 2 points in M. And then at this point, we have first of all the spin spaces, and we have the tangent spaces, which we just defined. And then we want to construct a mapping, like the spin connection. This should be mapping from Sy to Sx. And similarly, the metric connection, which we note with this nabla, should be mapping from Ty to Tx. And they should preserve the corresponding inner products. So this here should be like unitary with respect to the spin scalar product. And this here should be isometric with respect to this Minkowski matrix on the corresponding spaces, which I denote like this. So this is kind of the goal. And how can this be achieved? And the answer is, well, it can't be achieved in general, but we need one more important assumption, namely that the points x and y should be properly time-like separated. What does this mean? And this is really like a stronger notion of time-like separation. So first, I mean, if x and y are space-like separated, I don't see how one could do it. So they need to be time-like separated, but they need to be a little bit, we need a little bit more. And the definition is as follows. I mean, so x and y in M are are properly time-like separated. If the closed chain, let's just write it like this, xy no, in fact, that's not what I mean. It's better to work with this fermionic projector picture. So if AXY, which is defined as P of xy times P of yx, so this is like this mapping from the spin space to itself. If this mapping has strictly positive eigenvalues, and definite eigenspaces. By definite, I mean that they are either positive or negative definite. So this tells us already, I mean, that there must be one eigenspace which is positive definite of dimension 2, and there must be another eigenspace which is negative definite also of dimension 2, and moreover the eigenvalue should be positive. And it turns out that if you have a definite eigenspace, then the corresponding eigenvalue is automatically real. And therefore, this definition implies that x and y are time-like separated in the way we defined it in our first lecture. Because then the two eigenvalues are real, so this is a consequence of the fact that the eigenspaces are definite. And also the two eigenvalues cannot be the same, because otherwise the eigenspace would be four-dimensional and it would no longer be definite. Okay. And it turns out that this notion has nice properties. Namely, first of all, yes?
So, I mean, you said it before, so, I mean, it's time-like separate means they're real, but they are not allowed to have the same absolute values, so it's clear that they're not the same.
Yeah, because I assume that they are strictly positive, so you can omit taking the absolute values. So you have two strictly positive eigenvalues which cannot be the same. Because if they are the same, then you have one four-dimensional eigenspace, and then of course the same holds for the absolute values. And
So which points are Minkowski select? If you take the Minkowski vacuum,
yes.
which points are properly time-like?
Well, it turns out in this limiting case where we got the correspondence of the causal structures, time-like separation also already implies properly time-like separation. So if you compute the eigenspaces there, which we didn't do here, it turns out that they are really definite eigenspaces. Well, in some sense, you could say maybe this is the correct notion of defining time-like separation in the first place. I don't know, but I mean the other definition has the advantage that it fits better to the causal structure encoded in the Lagrangian. But I mean, this is really like what you need in order to work, what you need for proof, what you need to work with in the end. Okay, the nice properties are, first of all, I mean, this is again symmetric. So I mean, like if x and y, so x and y are time-like separated, then also y and x are time-like separated. In other words, if axy has these properties, then ayx also has these properties. Okay, so this notion is symmetric in x and y. In x and y, and just the idea, I mean, then it's like a simple computation. Suppose you take a eigenvector of axy, and lambda is strictly positive. Then there's a simple way of constructing an eigenvector of ayx, namely ayx times v is equal to lambda times v, where v is defined by we just take p of, let's see, p of yx times u. So in other words, the kernel of the fermionic projector maps the eigenspaces onto each other. And the fact that the eigenvalues are positive implies also that the positive definite one is mapped to the positive definite one and the negative definite one to the negative definite one. And this is why this notion is symmetric. Okay, now why is this useful in the constructions? Now suppose that x and y are properly time-like separated. Okay, so this means we have, like, say here x and here we have y. And then the nice thing is that this axy has two eigenspaces. One is positive definite, one is negative definite. And then we can introduce an operator which is called a directional sign operator, vxy, which has the property. So again, this is like a mapping from Sx to Sx. So let's write it like this. Like this is again a symmetric operator, linear operator Sx, with the properties that v of xy has eigenvalues plus or minus 1, and the eigenvalue corresponding to plus 1 is the positive definite eigenspace of axy, and the eigenspace corresponding to minus 1 such that the eigenspace corresponding to plus 1 minus 1 is the positive negative definite eigenspace of axy. And this is really why this construction is useful, because we have another sign operator to our disposal, and this is called a directional sign operator. So this means like now at the point x we have like two sign operators. The directional sign operator and the Euclidean sign operator, and then the hope is that this determines a unique Clifford subspace. Okay, and first of all, maybe the naive idea would be, well, I just try to find a Clifford subspace which contains both sign operators. But in fact, this does not work because we don't know that the anti-commutator of Sx and Vxy is a multiple of the identity matrix. So this will not be the case in general. But it turns out that there is like a canonical, that there are distinguished Clifford subspaces which are defined as follows. In fact, I don't give you the detailed definition, but I just tell you roughly speaking what they are. And we need one additional assumption at this point, which is also a bit kind of technical. So there's a kind of lemma of the following form. Like if the commutator of Sx and Vxy has maximal rank. So this means has rank 4, which is kind of generically satisfied, but it excludes some specific, whatever, some kind of, well, it includes some special cases, or like degenerate cases, let's put it like this. So if this has rank 4, then there are unique Clifford subspaces, and they can be expressed as follows. I mean, first of all, there's a Clifford subspace called Kxy. So this is a Clifford subspace which contains Vxy. And then there's another Clifford subspace called Kxy. And this is in fact a Clifford extension. In other words, this contains Sx. In other words, is a Clifford extension. Okay, and somehow what is the method of constructing those? Basically, I mean, like if this commutator is a multiple, if the anti-commutator of the two matrices is a multiple of the identity, it's clear what to do. Then you just take the Clifford subspace which contains both operators, and in this case there's in fact like a unique one, and this is just the same. This is the same as this one. But if the anti-commutator is not the identity, then the idea is kind of to project one of these two sign operators onto the other, kind of, and this gives you then a unique way of getting these Clifford subspaces. Okay, anyway, I mean, these computations, this is a little bit, well, it's not difficult, but you have to do some computations with 4x4 matrices to convince yourself that this is really how it goes. Okay, but now we are kind of in business. Now it's clear what to do. Well, let me just explain this kind of graphically. So we have the point x and we have the point y. So then here we have a directional sign operator. I just draw it as an, well, this is just, well, maybe I should not even draw anything. So here we have like v of xy, so this directional sign operator and the corresponding Clifford subspace kxy. Similarly here we have a directional operator vyx and the Clifford subspace kyx. And the idea is now to construct an operator which is then dx, y, so this maps now sy to sx in such a way that these sign operators are mapped to each other and also that these Clifford subspaces are mapped to each other. And it turns out that there is a unique d of xy which has a specific ansatz, which is of a specific form. And the way, let me just write this down. I mean, I agree, maybe this is a bit too complicated for what we should do here in the last minutes of the school. But let me just explain how this goes. I mean, the naive idea would be, well, we just take a polar decomposition. So this means we take the axy to the power minus 1/2 times p x comma y. So this is like kind of a unitary operator. I mean, this is just what you get from the polar decomposition. But it turns out if you take this, then this d of xy does not have the desired properties. And what you need to do is now you put in here an additional phase factor, which has the following form: I phi xy times vxy. And then you choose the phi appropriately. And then there is a unique phi under the above assumption, which lies in a certain interval. I mean, it's defined up to, I think, up to modulo pi. It's uniquely determined, and then you have to say in which interval does it need to be, and so on. So this is like the ansatz, and then there is a unique phi of xy, again provided that that this angle here is not just equal to whatever, what was it again, pi over 2. Let's see, on the no, this is kind of the unitary part. I mean, you can think of it similarly, the axy, this is something like, this is like p of xy times p of yx. And so you can also say this is just p times p star. And then therefore so we have something like p times p star to the power minus 1/2 times p. And this is in fact the unitary part. So you see, because well, suppose p is a multiple of the identity matrix, then this power minus 1/2 just cancels the factor which comes up here. Okay, so I mean here one needs to assume that the phi which, I mean for the phi which now has the desired relation, so the desired relation is that if we take kxy and now we kind of parallel transport it in this form, that this should be equal to kyx. So here we go from the spin space at y to x. Then this gives us a subspace, and then we map back. So this gives us a new subspace, and they should just be mapped to each other. And this equation then holds for a phi. There is a phi which is unique up to multiples of pi. So also up to multiples of pi. And then we have to assume that this phi of xy, in order to make this unique, we assume that this phi of xy is not, that pi over 2 is not the phi which satisfies this condition. There's always one. But if it's pi over 2, if pi over 2 satisfies this, this is the case which we want to exclude, because we want to have the unique connection. And then we have all kinds of conditions which and if we collect all these conditions, they go under the name spin connectable. So 2 points are spin connectable if they are properly time-lag separated, if this commutator has maximal rank, and if the angle which comes up here is not pi over 2 modulo pi. Whatever these conditions are, I mean, of course, some of them are kind of technical, but it turns out if you look at this in Minkowski space or on a Lorentzian manifold locally, then points are spin connectable if they are time-lag separated and sufficiently close to each other. So this is kind of the statement. Okay, now I should say, since we now have like this here also defines as a corresponding mapping of the tangent spaces. Or a vector, an element here, we can just use the kind of compose it with these spin connection, and then we get like a linear operator in here. So we get a mapping from kxy to kyx at the same time. Well, and this is not quite a tangent space because these are no Clifford extensions. So then one has to construct a mapping which goes from here to here. This is what is called like synchronization maps. And then you get into the tangent space, and then you can, well, and then you get the corresponding metric connection. So I think there's no point in entering the details. I just wanted to say, kind of the problem is somehow, what makes things a little bit complicated is that one has to work with different Clifford subspaces, different Clifford extensions, and then one always has to properly identify them using mappings. And there are these synchronization maps. And there are also additional maps which I'll explain now, which are called splice maps. It turns out that this is really something which is needed because otherwise you don't get the correspondence. Yes?
I looked at the stuff before, and even so you like the velocity now, so maybe I'm not sure how many people are still following what you're doing.
Well, of course we can, I'm almost done. Don't worry. I just want to say that there are these splice maps, just briefly what they are, because, and then I can state you what the main result is of the PhD thesis of Andreas Grotz. So the point is the following. Suppose we want to compose such spin connection. So we have like here xy, and then so we want to go, first of all, we want to go like this. So then we have like here dyx, which maps from here to here, and then we have here dzy, which maps from here to here. So this is like here sx, sy, sz. So the problem is, suppose we are at the point y, that we are working with different Clifford subspaces here than here. Because first of all, here we are working with this Clifford subspace K, which also was on the blackboard just right now. So this kxy, and in fact, since we are at the point y, so this is kyx. This is like the Clifford subspace which we work with when we construct the spin kind of the parallel transport from x to y. If we go from y to z, we work with a different Clifford subspace, which is kyz. And now one has to map one to the other, and this is done by this so-called splice maps. So whenever you compose such parallel transport, suppose dyx, and then we have here d from x to y, and now if we go from y to z, here in between you have to plug an additional operator which is called uy, and then we have to go basically from x to z. So this is like here the splice map. But I agree, this is a bit too much, so we don't want to go into the details. So let me just finish by saying what. No, we just gave it this name. If it appears in mathematics already, we okay, fine.
Maybe you can understand that you somehow want them to be close together, that someone has to transform something like this choice.
Well, yeah, somehow that's the way to think of it. If you construct this this parallel transport, you work in a specific Clifford subspace, and this depends on what x is. Although all you, I mean, you are working at the point y, say there's one Clifford subspace which is kind of corresponds to x, and there's another one which corresponds to z. And you have to kind of transform on one frame to the other frame. So that's what it is. And we just came up with the name because we did a Google search and it wasn't used yet, so there was no problem. Okay. And then now what is like the statement? In which sense does this correspond to the Levi-Civita spin connection? So this works as follows. So suppose we take a Lorentzian manifold, Mg, and then we construct the corresponding causal fermion system, which we denote by M epsilon. Say, so this is like the space-time of the corresponding causal fermion system. Okay, and again, I mean, the question is like, how do you choose the subspace H? We just choose it as the negative frequency solutions at some on any fixed Cauchy surface. It doesn't matter. So then, okay, so this is what we do. And then we have here a point x0 or q, and here's the point p. And this is like a time-like curve. And then we subdivide this curve into smaller pieces. So we choose here x0, which is equal to q, and then there comes x1 and so on, and there comes xn at the end, which is equal to p. Okay, and then the statement is like, and this is done here on a scale, let's call it delta. And if delta goes to 0, so if we take sufficiently many of such intermediate points, then always the adjacent points here are properly time-like separated. So this means this spin connection is well defined, and we have to work with this spliced spin connection. And just compose it. So we just take, so we go from, this is why we put these brackets here. This is like what the splicing is good for, x0, x1, d from x1 to x2, and so on. And the last step, we go from xn minus 1 to xn. Okay, this is something you can do. And this is like a mapping from the spin space here to the spin space over here. And now these spin spaces and the spinor spaces and so on, they are identified similar to what we explained, what we did like the first day. Now you can also consider the Levi-Civita connection. We'll just call it like this. The Levi-Civita connection from Q to P. So this is just the Levi-Civita spin connection. And then it turns out that these agree if we've let first epsilon go to 0. So epsilon is like this regularization length. And then we let delta go to 0. And it does not coincide completely. So there is an error term even if you do this. And this has the form of an ordered exponential, which is now the integral 1/6, the integral along gamma. So gamma is like, let's say this is the name of the curve here. And then we get here 1 over m squared minus the scalar curvature over 12 times, and then there comes here the derivative of the Riemann tensor along the curve. Okay, maybe I just write here dot, 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 because maybe there's no point in writing out the details. There's still a parallel transport and a parallel transport here, and there are these indices here somehow contracted and so on. So this is the statement. Well, and this means it does not quite coincide. There's a correction term, but it turns out that if you think of physically reasonable, well, like the physical space-times are like where we live in, I mean, then length scale on which the Riemann tensor comes into play. So this is like cosmological scales. It's much larger than the length scale determined by the mass, which is like the Compton scale. So therefore, this is like an extremely small correction. And in this sense, one can say that things agree. You can say that they agree. Okay, yeah, and obviously, I mean, it's important to take the limits in this way and so on, but maybe that's not so essential. Okay, so maybe this is like, well, this is basically all I wanted to say, and also it's already time is out. So in any case, I wanted to thank you very much for your interest and your patience. And I'm also grateful for all the comments you gave me and also the interesting discussions and so on. I mean, there are a few things I wanted to tell you before you leave. First of all, I mean, if you have any comments on the book or whatever, or find typos, errors, whatever, just let me know. I'm grateful for any feedback. And then just a few organizational things. I mean, some of you asked me if it's possible to get like a certificate that you were here for whatever reason. I mean, there's no problem if you want something like this. Just send us an email, and then we could just say that. So we will set up a letter, and this is something we could send to you. And moreover, I mean, some of you also, in case you like what we did here and you are interested in maybe doing something related or want to work in our group or whatever, I should say that, I mean, unfortunately, I have no positions in my group right now because they are all filled up. But there are possibilities to apply for funding like stipends, research grants, whatever. So in case you are interested, just let me know, and then we could talk it over and think about how this could be arranged. And then there was there something else? I mean, in any case, I wish you a safe trip back, and thanks for coming. And I think there was something with a picture. Someone wanted to take a picture of the group. Should we do this now? The group picture.
So what about, we could do the following, I mean, we could meet outside in 10 minutes.
Yes.
And before we go to the Mensa, we make the group picture.
Okay, this sounds good.
Out there somewhere.
Okay, so let's just meet at like 12, or let's say
Take